Hi, I'm Elaina Landrum. I'm in Professor Schatz's Physics 2 section, and this is my Lab 1 video presentation. The main concepts used in this lab were Coulomb's law to find electric force and relate it to electric fields, conservation of momentum and force balancing, and Newton's third law. The objective of the lab was to learn more about how point charges, electric forces, and electric field vectors all interact with and impact each other. My final calculations and results are listed. In section 7.1 of this lab, I observed that the two U-tapes were attracted to each other, meaning that one had a negative charge while the other had a positive charge. When a U-tape interacted with other objects, I noticed that each U-tape was attracted to neutral objects brought near it, which shows that the U-tapes induced an opposite charge in the neutral objects. Moving on to section 7.2, since the plastic pen is most likely to pick up a negative charge, a positively charged U-tape should be attracted to the charged plastic pen. If both the pen and the U-tape are negatively charged, they will repel each other. A neutral U-tape will either not interact at all with the charged pen, or it will be attracted to it due to an induced positive charge in the tape. In my experiment, the U-tape was attracted to the charged plastic pen, so the determined sign of charge on the U-tape is positive. For section 8.1, since the momentum is not changing, this means tape B is not moving. Therefore, the net y component of the force on this tape must be 0. The only vertical forces exerted on the floating portion of tape B are gravity and the electric force of the tape underneath it. The free body diagram of the floating tape is shown in the top right corner. The two vertical forces described previously must have the same magnitude and opposite directions, as shown by the arrow lengths and directions. The equation for finding the gravitational force is F equals ma, so to determine this, the mass is needed. The mass of the piece of tape is recorded to be 0.152 grams. Since the floating tape B is motionless, this means the net force acting on tape B is 0. Because both the electric force and the force of gravity on tape B are the only forces acting on this floating tape, this means the magnitudes of those two forces are equal. The charges on each piece of tape are hypothetically the same since they are the same size, shape, and material. So after we set the magnitudes equal to each other, we can rewrite the two different charges as just the charge of tape B squared. Then we can rearrange that equation to solve for the charge of tape B, which is calculated to be 1.802 times 10 to the negative 7 coulombs. For this section, I used the charge of the tape to find the number of excess or deficient electrons on the tape. The charge of the tape was calculated to be positive, so we know the number of electrons is a deficiency. Then we can use a ratio between a variable number of electrons and the charge to find the number of electrons deficient, which is 1.13 times 10 to the 12th. Using the length and width of a piece of tape, I calculated the surface area of the sticky side of the tape. Squaring the length factor of one atom gives the surface area of an atom. Dividing the surface area of the tape by that of one atom yields the number of atoms on the sticky side of the tape, which is 2.9 times 10 to the 17th. The ratio of electrons deficient to the number of atoms on the tape's surface is determined by dividing those two numbers, which yields 3.9 times 10 to the negative 6th. The main assumption these calculations required was assuming that each atom on the tape had the exact same surface area. If electrons were positively charged, the same transfer of charge would occur, it would just be different on the atomic level. The movement of electrons would result in a gain of positive instead of negative charge in the object they move to. It's important to not touch the tape too much because it can lose some of its charge when it interacts with other objects too much, making it less attracted to other charges. I molded the concepts from the function I wrote in Lab 0 to this lab. I know the force of gravity is equal to the electric force, which is equal to the electric field vector multiplied by the charge of the particle. So I substituted the electric field vector equation into the electric force equation, yielding electric force equals 1 over 4 pi epsilon 0 times q squared over r magnitude squared times r hat. Since q is the only unknown in this equation, I rearranged to solve for q, then used that value to find the electric field vector. The model computed a charge of 2.52 times 10 to the negative 9 coulombs. For this computation, I did have to ignore air resistance as this would have been another force acting on the tape and thus would have had to be taken into account during the equilibrium force balance. I also had to treat the long piece of tape as a point charge, not as an evenly distributed charge along the length of the tape. This ruled out the complicated reality that charged particles on one tape interact with different charged particles on the other tape. Overall, this lab emphasized how electric charges, forces, and fields interact and change in the presence of each other. Coulomb's law, as well as Newton's third law and the concept of force balance, were all very integral to my understanding of this lab and to the knowledge I gained through the experiment. Overall, this lab emphasized how electric charges, forces, and fields interact and change in the presence of each other. Coulomb's law, as well as Newton's third law and the concept of force balance, were all very integral to my understanding of this lab and to the knowledge I gained through the experiment.